So in this module, we have actually studied quite extensively about the inverter, right? That's the only logic gate we have looked at in this entire module. Question now is, what circuit can I construct with just an inverter? Okay, is there any useful circuit that I can construct with just an inverter? Of course, with NAND, NOR and other gates, you can make any logic. There's no doubt about it, right? Or if I just give you a NAND, it's enough. You can make any logic. But with just an inverter, what can you do, right? So it turns out that there is one interesting circuit as follows. Right? I have a chain of inverters like this. Now, what if I just connect the output of the last inverter back to its input? What do you think will happen? Right? So what happens if n number of inverters, right? 1, 2, n. If n is 2, what will happen? It will basically just remain at whatever state it comes to, right? Because of noise or whatever, if there is a 0 at the first input, then the output of the first inverter will be 1, output of the next inverter will be 0 again, that is fed back. It will remain in the stable state forever, right? However, if there are odd number of inverters in this chain, right? Then what happens is, let's say that this is 0, okay? Then this basically will make the output of the first inverter toggle to a 1 after some delay, right? So this will become 1, then this will become 0 after some delay, 1, 0, and then eventually, because n is odd, this will switch to a 1, right? And since it's fed back, right, this will now change to a 1, right? And this will switch to a 0, 1, 0, and this will keep going on and on and on. And not surprisingly, this is called a ring oscillator. Okay? Now, where is this circuit useful? So it turns out that when you manufacture a particular chip, send it for fabrication and you get it back, it's not guaranteed that all the transistors are going to come back from the fab as you had expected. Okay, so what happens is, I have a large circuit, right, like that microprocessor that I showed you, which has 8 billion transistors and so on, right? So it can so happen that when I manufacture these chips one after the other in a wafer, right? What is a wafer? Wafer is basically a circular thing where you have the diameter of this would be 300 mm. Okay, it's a huge silicon substrate. Okay, and on that, what you're going to do is, you're going to manufacture your chips like this. So each block here is basically a chip. Okay, so on a wafer you could have many chips like this. Some maybe 10K or something. Depending on the size of the chip, you can manufacture a lot of these. Now, this particular chip here, chip 1, need not get manufactured with the same specifications on the transistors as chip 999. Okay, so if you look at it, this guy will have one particular bias in the manufacturing. Okay, which means, what does that mean? So your level 1 model, like we spoke about, has a parameter VTH naught, gamma, this, that. That VTH naught can shift. VTH naught can shift slightly, right? Instead of 300 millivolt, it can become 350 millivolt, right? All the transistors in that chip, by the way, that's what I mean here. Every transistor in this chip 1 can have a VTH naught of VTH plus delta. This magenta guy, every transistor in this can have a VTH of VTH minus delta, right? So it's not guaranteed that all the chips that come back from the fab are going to come back in exactly the same specification that you had manufactured with, that you designed it with. So the first thing you need to figure out is how different are these transistors from my intended design value. Okay, so what you do is, in every chip, right? So what you see here is, this is my chip. I'm going to put a ring oscillator like this. Okay, with some odd number of inverters. Typically this will be a very large number, because this, what's the frequency of oscillation, by the way, of this ring oscillator? Huh? What is F by N? No. So if the input switch to a 0 at time equal to 0, how long will it take for the input to switch to a 1? Huh? So let's assume that the delay across each inverter is tau. Okay. So what is the delay for the 0 to propagate across all inverters? N tau, right? N tau. Now, what is the frequency of operation? 1 by 2 n tau, because now that 0 has to become 1, 1 has to become 0, right? So if you look at the output of this ring oscillator, it will go like this, right? This is too clean a waveform, but it may even look like a sinusoidal waveform in reality, by the way. This delay for output to go from 0 to 1 is basically my n tau. This is another n tau. Therefore, the frequency of operation is 1 by 2n tau. Okay. So let's do a quick calculation. If n is 30 picoseconds, and let's say tau is 30 picoseconds, n is 11. What's the frequency of operation? Somewhere in gigahertz, right? The problem is, if I have a signal that is oscillating like this at high frequency, I cannot bring this out of the chip. What will come out of the chip is only somewhere in megahertz. Okay, so you have to do a lot of things to, first of all, get this signal out of the chip. Okay, if you want to do on-chip measurement, that's a different story, right? But if you want to get this out of the chip and make a measurement outside, then you have to slow this down significantly. So therefore, what people do is they choose very large n. First, so that the frequency itself is in some reasonable, it will still be somewhere in the hundreds of megahertz range, right? Further, what you do is you put a divider, frequency divider, right? By 2, by 4, by 8, and then you bring it out, right? So after all that, you can bring this oscillating signal out from the chip, okay? So therefore, you put a ring oscillator which has large number of stages, followed by a divider also. And you get this out on a pad. Okay, this will be called ring oscillator out. Okay, so you can observe this on an oscilloscope, right? Or the tester can do an automated measurement, whatever it is, and you can find out what the frequency of operation is. Now, if all your transistors have gone from Vt to Vt plus delta, what will happen to the delay? every transistor has got a higher VT now. So what will happen to the current first of all? It will decrease, right? VGS minus VT is where it appears. If current decreases, what will happen to delay? Increase, right? It's C delta V by I. You remember that expression, right? So therefore, the delay will now increase. Okay. So the ring oscillators are therefore used primarily as global process monitors. Okay, I'll tell you what global is. Global process monitor. What does global mean here? It means that every transistor in this chip has moved by the same amount, the VT or all the process parameters, right? It's not just VT, by the way. It could be the channel length, it could be the oxide thickness. Every single model parameter has moved in the same direction, and therefore this is called a global shift in process or manufacturing variations. Okay. Now, chips are now quite large that even within a chip, I could have these variations. Okay. So what are the origin of these variations first of all? Okay. Process variations. So you take a transistor, okay, and this is my gate N plus P, oxide thickness and all that, right? So first of all, we are now trying to manufacture physical dimensions of what order of magnitude? 14 nanometer, 20 nanometer and so on. Unfortunately, the wavelength of light that is used to do this process of lithography is 192 nanometer. It's much larger than the dimension that we are trying to manufacture. So how are these things manufactured? You basically make a mask and then shine light. The shadow that is cast is supposed to hide some places and expose the other areas. But because the wavelength is 192 nanometer and you're trying to do manufacturing of 14 nanometer, 20 nanometer and so on, you will have diffraction. Okay. So what happens is, it is impossible to manufacture a million transistors, right? 8 billion transistors are there in my chip and across the wafer also. Impossible to manufacture all of these with exactly the same length. So each transistor technically can come out with a slightly different channel length. Okay, this L itself can now change because of lithography problems. Other thing is, we derived the expression for the VT, right? You remember it goes as square root of Na, where Na is basically the dopant concentration of the P substrate. Now it goes as square root of Na. We made a big assumption there that every dopant atom has got ionized appropriately, right? Under the channel, we are assuming that every single dopant atom has got ionized properly. Now let us see, how many dopant atoms do you think will be there under the channel? Order of magnitude. 10, 1 million, 1000, 10,000, 10 power? Okay, let's now, what is Na by the way? Na is about 10 power 15 per centimeter cube. This is a typical dopant concentration. So I am asking you, how many dopant atoms are there under the channel? Order of magnitude. Yeah? Like, just say 10,000, 1 lakh, million, 10 power 6, right? Okay. Go back and do this calculation. Assume that the channel length is maybe 22 nanometer, width is about 44 nanometer, right? And you can assume this depth to be some even 1 micron. Go back and do it. You will find that the answer number of dopant atoms under a channel is about 100. 10 power 15 I know looks very large, but that's across 1 centimeter cube. If I take 1 centimeter cube of volume, I have 10 power 15 dopant atoms. This is a very small fraction under the channel. Now think about this. If I have 100 dopant atoms and 10 of them are not ionized correctly, which means there is a defect. They are not participating in terminating the electric field or whatever it is. They cannot give me a free electron. What will happen to the VT? It has to go up, because I have to put in more effort to get other dopant atoms to give me, more free electrons. I have to deplete the channel more and all that stuff, right? So when you start making the channel smaller and smaller and smaller, you also have this effect of random dopant fluctuation. Okay, so one is litho changes. Okay, two is called random RDF. Now suppose I had a long channel device. Okay, why is this not a problem in a long channel device? Suppose I had like 10,000, long enough channels so that I had about 1,000 atoms, dopant atoms under the channel, right? For 100, I said 10 were failure because typically root n will fail. So if it is 1,000, what is root n? 30, right? Somewhere 30, 40. Now in 1,000, if 30 fails, nothing really changes, right? So this random dopant fluctuation is a big problem only for these minimum size devices, very small devices. If I have a large width also, this effect will go away. Okay, so in fact, the standard deviation of VT due to random dopant fluctuation goes as 1 over root of L into W. Which means that if I have a larger area, right, like I told you, it means I have 1,000 atoms. In 1,000 atoms, if 30 fail, not much will happen, which means that the standard deviation, right? So if I take 10,000 devices and plot the histogram, I'll get a spread in the VT, right? If I plot the histogram, the VT will look like this, right? In a Gaussian shape, and somewhere here, this is my sigma VT. Sigma VT goes as 1 by root of L into W. So the variations come down if I have a larger device. Okay, so the source of variations are so many such factors. Okay, and therefore I could have variations between two wafers. Between two dies on a wafer. Like here, chip 1 and chip 2 can have different parameters. Within the chip, I could still have variations, which means that the ring oscillator sitting at this corner will be different from the ring oscillator sitting at this corner. Right? So typically what people will do is they will put ring oscillators in multiple locations on the chip. If it's a big chip, okay, they'll put one arrow here, and maybe one arrow in the center also. And all of these will be accessible through pads. So the first thing you do is get the chip back, measure these parameters of the ring oscillator. If the frequency is not as what you had thought it was, it means there is a drift in the process parameters. Then you can correct for this appropriately, which means that if you know, for example, that all transistors have become slower because VT went up, then I can increase my VDD slightly. These corrections can happen. Okay, so ring oscillator is primarily used as a process monitor, both for within die variations. This is called a within die variation. Within the die, two different points can have different variations, right? It is also used as a global process monitor in the sense that every transistor on that die will basically have the same variation, but it can change from die to die. Okay. Now the other thing is, this is from your designer's perspective. from the fab perspective, I need to guarantee to the designer that my process is not shifting over time. It means that I have told you that the VT is going to be at this particular value, the current will be at this particular value, and so on. Now, with time, if this just keeps drifting away, that's not good. So the fab also has to monitor this, right? So how does the fab do it, right? Because remember, real estate space is very, very, very expensive. So for example, the fab cannot say, look, I will use this one particular chip to figure out if my process is correct or not. That's too expensive. You're wasting very expensive real estate space. Also, by monitoring just one corner, it's not going to help. I need to monitor it everywhere, right? So what the fab does is, in this wafer here, this is actually the place where the wafer will be diced. Means you're going to cut it, right? You will cut it on these directions and send this chip back to the customer. But before you cut it, you have access to that space. Okay, this space is called the kerf. All this is for your information, by the way. It's not like, I'm not going to ask this somewhere in the exam, so that you just get a complete picture of what happens from the fab and the designer's perspective. This kerf is where I will cut. So what the fab will do is, in this kerf region, they will put their ring oscillators here. Multiple ring oscillators in all kerf regions. So the fab, what it does, it manufactures a wafer, gets all the dice, then they make measurements on all these kerf structures. If the process has shifted significantly, it's a problem, it's a red flag. So the moment they see that the process variation is more than the acceptable limit, they will have to go back and debug and correct the manufacturing process so that it doesn't continue, right? So you make measurements here, make sure everything is fine, and then you cut it. Ring oscillator, it doesn't matter after that, because once you have made the measurement, you can as well clear. So it's interesting that a simple circuit with just inverters actually has so many uses. Okay, so it's sort of a brief overview of what process variations are and why you have to deal with it as a designer. Okay, any questions here? Okay, so we'll stop here. I'll see you tomorrow at 9. Thank you.